Welcome everyone to this episode of the AFMS seminar series. Our guest speaker today is Associate Professor Rowan Gollan from the University of Queensland. Rowan's main research interests are in the modeling and simulation of hypersonic flows. He is currently a lead principal developer for the open source gas dynamics toolkit and is known for his work on his flagship solver, ALMER, which I believe he will be talking more about today. So thank you, Rowan, for accepting our invitation. It's all yours, and we would love to hear more about your work.
Excellent. So thank you, Zade, and thank you, Javed, for the invite to speak at the AFMS seminar series. You see my title here, so to connect to the fluid mechanics community, I do a lot of research into high-speed flows, hypersonic flows. These are fast and often shock dominated. And we do modeling and simulation in our group, and we've built up a collection of tools, including a full suite tool, 2D, 3D simulation code based on the finite volume method. And what I want to talk about today, or kind of dive deep into, is how we've been expanding the flow solver to be part of a CFD-based aerodynamic shape optimization routine. And we've solved a problem. We're not the first to solve it. We solved a problem of many parameter optimization by using something called the adjoint method. And that's my intent to talk today. So my name's on this first slide, but if I do this, I'd also like to get right up front the acknowledgements. On that first dot point line, this work really started with the PhD thesis of Kyle Dam. He's since left the group. And the first name on that line is Reese Otto, who's with the group now and continued the work of Kyle. So I'm going to be talking about a lot of their work and contributions. But none of what we do here happens in a vacuum. So I also want to list current and recent members of the team because there's no lines of code that don't get touched by someone at some point. So today's talk is going to be specifically about that aerodynamic shape optimization. To give some context, I'm going to speak a little more broadly about this flow solver ALMA, as Azadeh mentioned in her introduction. And then I'm going to talk about our approach of adjoint-based optimization. So I've given a little bit of a recipe. I'll give an overview. I'll talk about this thing in particular called the adjoint method. I'll explain why we need deep convergence and how we've achieved that. And then what really kind of pins to our more recent work in 3D and the outcomes from Reese Otto's PhD thesis is how we've tackled design parameterization in 3D. And we'll look at how we can use both parameterization, the way we do it, to do grid deformation. And on the right, the image kind of is the spoiler. This is where we're going to finish the talk and talk about a particular result, a demonstration of our method, which is maximizing this lift to drag ratio of a hypersonic lifting body subject to a volume constraint. And if your eyes are good, you can see the optimizer cheats a little bit to get there. But the goal of this is not only to maximize lift to drag, but also to contain a payload of a certain shape. So for people who aren't familiar with the code, we've been developing this compressible flow code in Australia for more than 30 years now. It didn't quite begin life in Australia, as you see there. It started out at NASA Langley. And I think I noticed a former colleague or a continuing colleague, Jeff White. So he was also around ICASE at the time when the very first version of this code you'll see today was written. Version's a strange word to use here. Lines of code have changed. We've switched languages twice, C to C++, C++ to the D language. And we had different branches of 2D and 3D along the way, but these all merged in the November of 2008 to be a single 2D, 3D finite volume flow code. Our switch to this deprogramming language noted there began in about 2014. And today we're in the midst of our ALMA version 5 release. The local people, the developers are all working or mostly working with Elma 5, and we're trying to get this ready for broader public adoption. Just as a little interest here, there's a waffle plot showing our division of languages. Some people like to see how the code, and that's not just the flow code, that's the entire gas dynamic toolkit. And the image on the right shows you can go find us on GitHub. This is a long list of features and capabilities. I think the point I want to make is that the problems we need to tackle in hypersonics are often multi-physics ones. Hypersonic vehicle designs are driving, not the only parameter, but are largely driven by heat transfer considerations. So thermal management's a big deal. So it's not just one thing to get the aero right. You need to then know how that heating is soaking into your structure if you want to design for long-term survivability. That's one aspect of multi-physics. It's not the only aspect of multi-physics. Through combustors and in hot shock layers, we can get kinetic effects. We also want to look at problems of moving boundaries and moving grids. So I picked out a few things in orange that will have images on the following slides. And that's why they're shown there. The one right here is that coupling of fluid to solid. So in this picture here, we have the bolt to flight article, and we've actually simulated a portion of its trajectory, and Elma has solved for both the fluid and the solid domain in this. We're loosely coupled in time, but the time evolution in the solid domain is time accurate in these simulations. And at intermediate periods, typically about 0.5 seconds along a trajectory, we recompute the flow solution and use that as our heat boundary into the solid domain. So we do big calculations. To stuff we show today in the optimization all fit on a single fat modern workstation. But for some of the really fluid physics types investigations, we need to scale to thousands of cores to do our work. So that brings us to what is Elma used for. Began life as experiment support. And if we look at the bottom left, we see a nozzle. So this kind of brings everything together. The code was used to design the nozzle. We used the code to analyze the flow that comes out of the nozzle. There's shot-to-shot variations. This nozzle, I should explain, is we're looking from the throat forward. It's a hypersonic nozzle for a reflected shock tube facility, shock tunnel facility in this case. So the simulations support experiments by actually characterizing the flow in the facilities. And then we also use the code to support the business end of the experiment, so to speak. So on the right here, I have an animation. This animation of double cone is not, in this particular case, wasn't a particular physical experiment. People have studied double cones. But this one was a numerical study that looked at many configurations of those ramp angles to try and find where these flow features are steady and where they're unsteady. Clearly, this one falls into the unsteady portion. So that was a use of Elma as, I might call it, flow physics investigation or a parameter sweep, where the flow code replaced the wind tunnel on that point because just a far more efficient way to sweep a large parameter set. And in the top right, some of our high temperature gas dynamics work. This is a simulation of the Fire 2 capsule, a demonstration of our 2 temperature, 11 species type modeling that allows us to work in the real high enthalpy flows. Some other things we've done recently, we've applied the code to scramjet flow paths. This is supporting a project that was looking at is there a benefit to oxygen enrichment in a scramjet flight mode? And the use case for that might be at the edge of your atmosphere where there's enough oxygen to work with, there could be benefits to carrying a little bit on board and continuing how far you can use your scramjet on part of an access to space trajectory. So we can see contours of Mach number. We can see where hydrogen's being injected here, and where we're going to red, H2O mass fraction is going to indicate burning's occurred. So because we've produced water. We also use the code to look and probe fluid physics. So here's an example, not so much about the physics itself, but a demonstration of a higher order simulation. And what I'm showing here is the code is simulating with a fourth order scheme on a finite volume grid everywhere except where the shock detector is enabled and the code blends back to second order in those places. But what this allows us to do is some high resolution work. And the shock detector blends between 0 and 1, and we actually use that as our blending between the fourth order method and the second order method. So that's applied to problems like this. This is a shear layer that demonstrates mixing. This is one of our first attempts at direct numerical simulation. And this is the kind of work that informs turbulence chemistry models in RANS. So this is a DNS with reacting flow. And from that, we can tune our ideas about how to build some more design appropriate models for the RANS world. And a final example on the physical modeling, some very recent work is coupling ELMA to material response code. Here you're actually seeing the material response, but we've computed a flow field with ELMA to inform the heat transfer into an ablating material. So we're getting to see some recession due to the high heat flux from the shock layer around a blunt body. So that now brings me to the main part of this talk. Another thing that interests me is the design of hypersonic vehicles. And it's been my main motivator for this adjoint-based optimization work. A fair bit earlier in my career, I worked specifically on these shape transition inlets. And at the time, so I'm pointing to the pinkish color here that's hiding into the vehicle. And on this side, the very light pink, you can see the tail end, the exhaust nozzle of these scramjet modules. So that work I did at NASA, we were looking at a way to optimize these flow paths, particularly the inlet. We had something like a feature-based optimization and a little bit of geometric parameterization. It was useful, but it was also limiting and very case specific. And also while I was working at NASA, I got to see another branch using adjoint-based optimization. And this kind of really interests me. So that started me on this path of looking about how we can use this in our code. To point out some of the engineering challenge, what I'm showing here, and this was taken from Alex Ward's thesis, he's colored these things to show how he's going to account for the force. But the point I want to make is that as an inlet designer, we're really concentrating on its role as compression to the combustor and wanting to maximize that performance. But the challenge and what keeps hypersonics exciting is how tightly coupled all the aerodynamics is in one of these vehicles. If we look over to the right and we look at the lift component, we see those inlets, those things that I'm specifically worried about their compression, are actually contributing a rather large amount of lift to the vehicle. And that I don't actually think about during design. It just comes out, and then we have to account for it later on. In fact, you'll even see the inlets provide more lift than the wings. That's not to say that inlets are a great wing shape. That's more just to say that we really don't need big wing planform areas on these vehicles that are flying at this speed. And as we'll conclude the talk today, we're going to see a vehicle with no wings at all, just a pure lifting body. But I want to make a point that this is the kind of challenge from the engineering side. We can attempt to design things in isolation, but they are highly coupled, and it would be good if we could get that coupling early on into our design process. The numerical challenge I want to talk about is these shapes are rather complex, and it would be desirable to use many parameters. But many parameters can be a bottleneck when you start to go to optimization workflows. So that leads me to this overview of how we do CFD-based optimization. And when I say we, this is not unique. This is a fairly standard flow chart for using CFD in the loop. You have a flow solver. We have one, thankfully. If you have a black box flow solver, and what I mean by that is you can't get in and alter the source code. You're going to need often derivatives of how your flow is behaving relative to your design parameters. So to just unpack this particular parameter here, dj/dd, J is some performance metric, some objective function. We often like to minimize it, could be maximized, but and we want to then, if we want to, most optimizers or an efficient way to use optimizers, if you do have gradients, is to take that performance measure and see its sensitivity to all your design parameters. And this is that bottleneck I was hinting at, because if you have many design parameters in a black box CFD solver, you're going to have to run many flow solutions, perturbing just slightly in each parameter, recomputing the flow, extracting your performance metric to build up that vector of sensitivities. And this is the thing I'm going to talk about that the adjoint method helps us with. But if we have sensitivities, you can see this is controlled by an optimizer, in this case, a gradient-based optimizer. If we decide we're not yet at a good enough shape, we're going to apply some shape deformation. If we deform the shape, typically the surface that we're interested in, there's a subsequent follow-on where we'll need to deform the mesh. Now we have a whole new design iteration, and we start again. You see some inputs. We have to pick a baseline geometry, and we have to parameterize it in some manner before we can get started on that. So the next few slides are going to talk about work we've done on these things. We won't talk much about the optimizer because it's not our work. We use standard optimizer packages, but we will talk about the CFD and the related work that we've done on this. Here's the maths bit. I want to give you the flavor of the problem we're solving with the adjoint. There's not enough here to show you how, and it's a different talk to show you all the mathematics. But here's the flavor of our bottleneck. If we start with some objective function that is parameter of our grid positions and our flow state, and in turn the design variables, we could expand that out, and we're going to have some sensitivity to our grid, and we're going to have some sensitivity to our flow itself. And the term here that I've got highlighted in red is going to be the difficult one. This is the one that's going to scale with number of design parameters. So does the grid, but we have ways to get around that. This one is going to involve us needing to do full flow solutions for each design parameter. So you can see the poor scaling if we want to go to 50 design parameters or 100 design parameters. And that's what I've noted here. To fill out one full sensitivity calculation, we're going to need n+1 flow solutions if we're working with n design variables. So here's the bit where I'm not going to show you the derivation, but I am going to show you the mathematical trick that's applied. The adjoint method hinges on augmenting this equation. You can do it via Lagrange multipliers. And you can show that you can relate at steady state to your flow residual. So we're going to have lambda t, and we're going to replace this term with this idea here. What this means is we now have to figure out these series of Lagrange multipliers, and these are what people call the adjoint variables. And we do that by solving this equation. So if people talk about the adjoint equation for a CFD code, they're often talking about something this. Now, if you look on the left-hand side, dr du is the Jacobian people are probably used to, happens to be transposed. So that's the first bit where I want to point out that having access to your code is going to be useful. You're going to need your Jacobian and all the entries, and this is the Jacobian at the final converged steady state. This is our AX equals B equation. So over here on B, the thing I want to point out is that your adjoint is conditioned against F. It's conditioned against the performance metric you're after. We set an objective function, so that could be lift to drag, but it's also conditioned against constraints. And if you have constraints in your optimization, you will also have to solve additional adjoint equations. But what do we get? So we have this extra mathematics. What do we get for this? What we get now is that we can get our sensitivity derivatives from just one flow solution and just one adjoint solution. Adjoint solution's a single shot matrix. We may have to precondition it, but we've got to solve it. It's not really like a flow solver where we can kind of iterate through in a time sense or a Newton sense. And the cost of solving that adjoint, it varies, but the literature will normally say it's on the order of the cost of one flow solution as well. For some of our stuff, it's probably smaller and quicker. So you see that's freed us up, and that's independent of the number of design variables. So I want to step a little to the side, but one of the things we needed to do to get there is that in that equation, I'll just go back 1 second. When we form this set of coefficients, it's really important you have a deeply converged flow field. Well, it makes solving this equation far easier. And so that's why people in the adjoint literature will often talk about needing deep convergence. So we got on the path of looking for deep convergence by implementing a Newton-Krylov method. The method is simple to state. Here is our Newton iterate. We're just going to find delta U, and delta U is an AX equals B type equation. Jacobian at level n. We're solving for delta U, and we have our residual on the right-hand side. So we want to move via Newton iterations towards a residual of 0. At each step of that, we have a linear system to solve so that we can get some delta U's. We'll use a Krylov type approach, and in particular, GEMRES algorithm. We've gone Jacobian free for a few reasons. It's very efficient on memory storage compared to other approaches. But the real reason for us is because we are a hypersonic flow code. We do need to handle many different types of physics. We don't have to have many different types of flux calculators, but it turns out that we do. And what we wanted was essentially a way to automatically differentiate. So we use complex step differentiation. If you use the GEMRES algorithm, you never actually have to form the Jacobian in isolation. That's the Jacobian free part. The GEMRES algorithm only ever requires Jacobian multiplied by the Krylov vector of interest. So what that means is that we can, and then one can approximate that Jacobian vector product with something called the fresh A derivative. That's where we use this complex step differentiation. Costs us a little bit in storage rather than just floats or doubles. We have the storage of the imaginary component as well. But the overhead of that is something like 60% in memory and also floating point operations relative to not getting converged at all. So when people sometimes balk a bit when you tell them the overhead, but the flip side to that is if we just work with real values, it's quite hard to get these methods to converge. So I've mentioned some of the advantages, some of the others I've listed here. Relative to some other iterative solvers, Newton-Krylov methods are strong, and there's a global dot product, so it kind of binds all your blocks together each iteration. We get implicit boundary conditions for free, essentially, thanks to that fresh A derivative. And the reason we went down this out of the starting blocks was that deep convergence. We need this, and we're not going to shy away from it for our adjoint work. But as just a general purpose steady state accelerator, we find it good, but there are some disadvantages. There are a large number of numerical parameters relative to some other methods. And the last disadvantage, I just kind of put that the global solve of this feels the effect of poor grid quality very, very quickly. This might be an advantage. It might be telling you your grid's not good, but other methods will kind of ring along and you'll wonder why. You'll often get pretty quick feedback from a Newton-Krylov solver, and that feedback will be in the form of stalled convergence. So we presented this Krylov work at the AIAA conference a couple of years back, and my little postage stamp images here. We wanted to show that it was useful in this hypersonic context. This is a cylinder. It's a 2-temperature flow, so that's what I'm showing here, the vibrational temperature. And on the right is wall clock time to convergence using the Newton-Krylov method as compared to point implicit. Point implicit might be a little unfair. There's probably better methods, but I didn't have time to kind of implement every other method that could live in between this space. And just to show it works in another context, we also looked at a hydrogen combustion test. Here is some supersonic flow coming in from the left. There's a little backward-facing step with some ignition of hydrogen. And you can see that it burns, and this was all on an unstructured grid. And again, we got really nice deep convergence on a test problem like that. So these were 2D, but we've since the oxygen-enriched scramjet you saw earlier, 3D has been done with this method as well. This slide is not particularly related to today's talk, but it does close out where we are with the steady state algorithm. We're really quite excited about this. It's our kind of newest algorithm off the block at the moment. If you're interested in pretty pictures, look to the left. When this animation restarts, we're watching a shock fit boundary. You can see it here. And this is all happening inside the steady state algorithm. If you're a CFD nerd and like convergence, you can look to the right and see the convergence plot. And we've shaded it by the different phases of our Newton-Krylov solver. So early on, we are in shock capturing mode. I think it's probably just first order, so it's the easiest type of shock capturing mode. Then we've moved to shock fitting mode, and we keep the code low order for stability and basically to try and get this shock boundary into place. And once that shock boundary is in place, we can switch to second order, which is going to clean up or give us better resolution for the same number of cells. And you also see it allows us to get into that deep convergence zone of the Newton-Krylov quadratic convergence. So this is going to be really useful for our high temperature blunt body work. So I'm going to return to this adjoint method, but to set the scene, a bit of history, I want to show you one of our early successes, and this was an outcome of Kyle Dam's thesis. And we looked at, we call it a redesign, or basically using CFD-based optimization to compare against an old experiment. This experiment here was a hypersonic inlet, as noted in the original photo. Flow direction is from right to left. P2 comes from the compression ratio. It's not the ratio, it's from the tip. It's the compression ratio from that first ramp into the combustor area. And why CFD people like it is this was a 1970s experiment, envisaged techniques to set up the geometry and viscous corrections, the best that was available to engineers at the time, by hand. Turned out those viscous corrections didn't kind of achieve what they wanted to do. And that's why the CFD guys get excited. So here is a simulation of the original experiment, but the experiment results also bear this out, and you can compare on a pressure rake across the inlet to confirm that. So here was the unexpected result. There was this undesirable shock that wasn't planned on, and it was essentially an effect of the viscous correction not being correct. So as a benchmarking exercise, there's lots of CFD people like to come in and do a deep dive on this part of the surface and see if they can redesign it. So we did that as well to kind of put our adjoint method in context. And you can see the result of the optimized design. It has removed the shock and achieved the target pressure ratio. That was the design. And in fact, I think the design was uniformity at this point. And you can see it's exactly what the optimizer does. Gives you uniformity at that point, achieving it. But what happens afterwards is not part of the metric. That's a good engineering result. On the right is a good algorithm result. And what we're showing here is these curves that just ring out are the kind of black box, the traditional finite difference approach. The one I said we're trying to avoid, where you have to keep reevaluating your flow solution every time you want to take a step. The curves that are converged much quicker are our adjoint method. And in this particular case, the ones in red are the only times we had to stop and do a flow and adjoint. So the intermediate ones are just steps in the optimizer, but it's only at the red points that the flow solver was invoked again. So if you count them up, there's something like 11 points. The other thing to see is we just tested the sensitivity of our design to how many parameters we use. So we tried it with 11 parameters. That's the 11 point, and with 20 points. We get essentially the same result, but the runtime convergence is also very comparable, which was the whole selling point of adjoint, right? That we should be able to go to many parameters relatively independent of how many we choose at the same cost. So where we are on the story, we talked about the adjoint method that's going to allow us to do this sensitivity calculation. I told you in particular about the Newton-Krylov solver, and I've demonstrated this all in 3D. But what I want to talk about now is our more recent work, outcomes from Reese's thesis on doing the shape and mesh deformation. So this was our step to doing 3D geometries. There's a number of approaches you can take to do surface parameterization in a geometric sense. And on the left, I've shown B-spline surfaces. So we have a representation of the thing as a network of B-splines. Another approach is freeform deformation. So in this, you have a cage, and then you look for parameters in a parameter space that map into that cage. You deform the edges of the hull, those red points, because they map to all the internal things, you have a corresponding motion. what we've done is combine the two ideas. Hopefully, like most hybrid things, you get the best of both worlds and avoid some of the pitfalls. So that's this idea of two-level freeform deformation. So what am I showing here? We have some aircraft. We're going to use B-splines to parameterize the surface. Those B-splines happen to have control points. They're shown in red. Now, rather than build a freeform deformation cage to connect to the surface, we're going to use a freeform deformation cage to connect to control of the red points, so our control points for the B-spline surfaces. And this has been used in a few places, but it's new for us applying it in this high-speed flow regime. So that's the approach Reese built. What it's meant is we're going to take it one step further. When we fit our B-splines, it's not going to be only the surface. We're going to try and fit a B-spline volume to the volume grid as well. And what this will allow us to do is if we move the control points for our surface, we get a subsequent deformation in the volume grid as well for free instantaneously. We'll see what that looks like in practice. Here's a fairly simple way to think about it. We call it our hypersonic bump. You don't see any flow here, but it's a nice intuitive test case. Here is a flat plate with some bump, and the optimizer is later asked to minimize the drag. So to minimize the drag, it flattens the bump. If it does something else, we scratch our head. But when it flattens the bump, we're pretty happy. But I don't want to talk about the optimization. I want to talk about this shape parameterization. So we build a mesh. We're going to fit the B-splines. Here, the blue is our surface of interest. That's going to be our design. But we're also fitting to the volume mesh at the same time with our B-spline volume. And now we're going to put that hull around the surface of interest. So these red points will become our design parameters when we're running the optimizer. So just to see that, we're going to deform the freeform hull as part of the optimizer is going to control these and say where the points should move. That has a corresponding movement to the design surface. That allows the entire mesh. We propagate that motion by an inverse distance weighting. That's simple enough and has worked for our purposes. And so now we get our mesh deformation as well. So how do we test this working? Well, we take a 3D thing and go try to do something axisymmetric and hope it holds up and hope that symmetry still applies. This is a test case people like to do in supersonic flow. What is a minimum drag slender body subject to a length and a base diameter constraint? So typical use case for that might be a nose cone. We've taken some baseline starting shape and allowed it to evolve. It comes to something very like a von Karman ogive, but not precisely the von Karman ogive. We've taken our work and compared it against others. You can see this is a cone for reference. There's some early work by Mason. That's the line in orange. Kyle's PhD, the one I talked about earlier on, which was all in 2D, he had a result from this. And then our most recent work in 3D, lines up with that and shows that we can do these simple type problems. And it's a real good test for that deformation methodology I showed a moment earlier. So that brings us to the main event, I guess, which is to talk about the lifting body I showed right at the start of this talk and how we can bring all these pieces together to do some aerodynamic shape optimization. But just to set the scene for that, I wanted to show a list of other work specifically CFD-based optimization. Some people familiar with this area might be thinking back to Kevin Bowcut's thesis. That was a viscous optimized wave rider. That wasn't specifically CFD, that was panel methods with viscous corrections. So I've tried to just narrow down this literature to those other researchers who've used CFD. So you can see a number of different configurations being looked at: lifting bodies, wings, and inlets. And I've put our work at the bottom. Various flow models have been attempted: Rand's models and Envisage models. That's the Euler. Shape parameterization across different attempts. And we sit here with this two-level freeform deformation approach. The grid deformation, I mentioned we deform the B-spline and then we propagate the other control points by inverse distance weighting, IDW. Optimization algorithms, ours is gradient based. It's this SNOPT routine. And interestingly, for me, or what keeps me excited about this work is we're now gone past 100 design parameters. We have 121 design variables for the lifting body we're going to look at. I mentioned this, so I'll touch on it briefly. This is the design problem we want to look at: maximize lift to drag ratio, but ensure that yellow payload remains inside the vehicle. And we've also subjected this to a length constraint as well. We do this with 121 design parameters, not all shown here. As a method, not as engineering, but as a test of the method, we've done this with Envisage flow, laminar flow, and turbulent flow, just to check that our adjoint can solve in those different modeling arrangements. And we've even done it with just a panel method, so that's a non-CFD method. Depending on where we're flying, I don't know where we fly in the altitude for this case in particular. It's probably turbulent, but it may not be turbulent from the tip, but that's a problem for another day to have a model that has transition. So here's the result. Here is our shape going through its design iterations. I'll talk about the shape first. You see, it starts with this body that came from an old DARPA project. And the optimizer is moving, for people who are familiar with the world of hypersonics, it is moving towards something that looks like a wave rider. And what it's attempting to do is separate the aerodynamics on the bottom surface from the top. And this is its attempt to maximize the lift to drag ratio. You can actually see that optimization history here. It's got out of sync. But if you look at the little inset plot, the blue is showing how the lift to drag ratio is improving with time. And the red is showing how well we achieved the volume constraint. We've multiplied that by 1,000. So the optimizer has some freedom to ignore the constraint a little bit, but that reins it in to getting back on the right path. This little bit here, obviously in the search space, it's decided it's doing okay, but can it look elsewhere? It looks elsewhere and decides no, and kind of moves back towards this. But this is pretty powerful. And what the other thing to mention is that this simulation, this whole design loop, was 4 days on a workstation. Now, 4 days is not overnight, but 4 days is pretty good for 121 design parameters, a 3D flow simulation, doing RANs and getting a result that's much better in terms of lift to drag than where you started. This animation is just going to show you some of the detail. You can see the red cage being those B spines near the surface, and you can see how the volume grid is also deforming throughout the design iterations. And we've kind of zoomed in on the nose as well. So we can just summarize those results. That's all I want to finish with on this slide here. Just took a few design iterations where we start lift to drag 3.4, some way along where we've improved quite a bit to 3.82. And by the time we're claiming convergence, we've got this lift to drag ratio of 4.14. But we can also break that down, and you can see that what the optimizer has done is actually reduced the lift quite a bit, but in a relative manner, it's reduced the drag even more by getting to that design that minimizes surface area and gets away from the flow that's only producing drag. So that brings me to, I don't have any great conclusions, but I will just finish on some future work. We're pretty excited with where we've got to, but our next steps, geometry-wise, it's going to be to increase the complexity of surfaces we can tackle. And going back to that original engineering challenge, that's going to allow us to work on combined subsystems. A combined subsystem, for example, might be both the forebody and inlet system of a hypersonic vehicle, because as I mentioned, forebody is some compression to your inlet system, and your inlet system is a large amount of your lift. And those two things want to do both. Together, they want to provide some lift, and they do want to provide the right compression. So it looks like a good synergy that could be explored with design optimization. Maybe designing the systems in tandem or at the same time will lead to a better outcome than treating them as separate systems that we have to put together. And on the physical modeling front, we want to step out of the perfect gas aero and move to include our high temperature gas effects. So particularly I'm thinking about finite rate chemistry effects and multi-temperature effects. This would allow us to look at configurations inside scramjet flow paths and also high-speed blunt bodies, re-entry bodies. So as I noted there, that would push us out of just the external aero in the Mark 5 to 10 regime. So I'll end at that point, and maybe I'll hand back to Azadeh. I don't know how best the questions are handled, but that's what I wanted to present today.
Well, thank you so much, Rowan. It was very interesting. So let's open the floor to questions. Please feel free to either speak up or type in the chat if you have any questions. And while we wait on that, I'm just going to ask something myself. You mentioned the combined subsystem optimization. So do you imagine this as a simultaneous optimization loop?
What I imagine no, I just imagine extending the geometry. So the line people usually use when they get to hypersonic vehicle design is that we're not designing a jumbo jet. You can't have one team work on the fuselage, one team work on the wings, and one team work on the engine and then just bolt it on. The whole thing is very coupled. And to answer your question, Azadeh, I was thinking of, I'm just trying to get back to the image, geometric coupling. So rather than just optimize an inlet system, can I look at a geometric coupling and actually have an entire parameter surface? I'm not sure if my mouse is showing, but for example, something that goes from a forebody all the way to the end of the inlet. Or you could look at it another way. You could say, can we do tip to tail combusting flow path that will both excite and scare some people in the hypersonic world. It's a big ticket challenge.
Yeah, no, thank you. No, that makes sense. And do you think, because you said the example took 4 working days, do you think this will gonna take much longer?
Working days include 24 hours, 24/7. Yeah, that's sorry, go on. Yeah.
Yeah.
Yeah, this is kind of a line that people have said. I am not a practicing design engineer, but there was a rule of thumb that it would be useful design turnaround times if you're doing this kind of exploratory design, if you can get an answer overnight. So if you can change something on your geometry, set your computer running, come in the next day. That's a useful turnaround cycle for this kind of vehicle design. So that's always been another drive. And I'll add to that, and you don't want to have to do that. We could get faster by going to a supercomputer. Small to medium enterprises aren't going to have access to supercomputers to do this kind of work. And it's also it's the kind of work it's not every day. You're not in the design cycle every day, so you're not necessarily paying for a supercomputer for just a portion of your engineering work. So that's that kind of rule of thumb. It's not evidence-based. It's just a thing that if you can get an answer overnight, it's a pretty good way to get feedback and move forward with your design.
Thanks. We have a question from Sean in the chats. So it says, thanks for the presentation, Rowan. I wanted to ask about your experience on utilizing different optimizers. In your table on cases in literature, several studies involve the BFGS optimizer. Do you find that a second order optimizer works well for a problem like this, or do you prefer to utilize an optimizer with a slower convergence?
All right, I'm going to give the first part of the answer. And sitting to my right in this room is Reese Otto. Reese, do you want to bring up the chat so you can have a look at the question while I'm answering? We have tried different optimizers, and we landed on one that was most robust. If I go back a step in Kyle Dam's work, I think because the design space was better behaved, we kind of just took the first optimizer out of the box, and at the time we were using Dakota, the base version, not the special one that you need a license for, and things just worked. As we got to this more complex design space that Reese has been exploring, we did have to look around for optimizers that were both robust, but then when they get close to convergence are efficient. So Reese is typing an answer to you now as well, that addresses the specific comment about second order optimizers.
Right. Do we have any other questions?
I have one question. Ron, thank you so much for your presentation. It was very informative. Actually, my question is about the optimization. So just wondering to know, what do you think about the reinforcement learning, machine learning? Because your flowchart that you presented is very similar to the reinforcement learning in the machine learning. So we have the CFD and we have optimizer. So what do you think? I believe that it's for the large scale simulation is a bit difficult because we need to define the different actually control points. But just wondering to know your thoughts.
Okay, so the machine learning, I'll try to answer it this way. It could be applied to this problem in a few different ways. You could apply it to the design space. You could say, I want to run a number of flow calculations, and this is like a surrogate model of some sort. And what I'm going to do is my surrogate model will be some neural network. So I think in that sense, I don't think this will be competitive with our method because you're back to that problem of just running a flow solver in many different places across the parameter space and then trying to fit it. In fact, it's probably a little worse than even guided surrogate models, because I don't think typical machine learning is kind of adaptive as it goes. Maybe there is, but I'm not a machine learning expert. But if it's just, here is all the data and now you need to train against it, you would have no information before you got started on how to space that data. So I think that would be inefficient. Now, if you want to go down a level, some people have argued that if you have a neural net solution of your flow field, and this is like the physics-informed neural network, that if you have that neural net to represent your flow field, then you get your derivatives for free because you can go through your activation functions. That might be interesting, but I think we're a long way of doing it on a complex geometry like this. From what I've seen for these high-speed flows with shocks, there's some progress on very simple shapes. And what do I want to say about that? Oh, very simple shapes, and the methods are too early, in my opinion. We don't have good guidance on how to set things up, and there's a bunch of tuning on hyperparameters for every single case. And that's on simple things. On these kind of 3D vehicles, we have very well developed state of the art. We can build good meshes. We know how the numerics works. So I guess they're my thoughts. My thoughts are right at the moment. I think this type of method, which does involve a bit of work and getting to know both your flow solver and the adjoint, but I think it's going to beat any machine learning approaches for quite some time.
Thank you.
USQ, do you want to speak up, or because we have a message from you in the chat?
Thanks for
Yes.
thanks for the talk. I was just going to ask a question. You mentioned with the Newton-Krylov solver that it was quite sensitive to grid quality. And so moving forward, I guess with more complex geometric shapes, do you have a bit of an idea where you want to take your mesh generation / grid quality in the future to do sort of multi-component geometries, and how that might work with the design parameters?
Yeah, okay. I'll answer in two parts. The first is just to clarify that the Newton-Krylov's probably not sensitive any less or more than our base numerics. At the end of the day, it's the right-hand side which is informed by the flux calculator using and the reconstruction using. So all it is that you're probably going to find it quicker. The Newton-Krylov's going to stall earlier. And that was the comment there. On the part about but your follow-on question was then, what does this mean for the complexity we want to solve? A detail I didn't mention today is that although we had structured grids here, we were actually running unstructured numerics. We have a technical back-end challenge that relates to how we use limiters. And when we use limiters on unstructured grids, they are decoupled in the code, and we're actually able to freeze them at some point in the convergence, and that allows us to get deep convergence. And we don't have that for our structured grid technology just because of the way the reconstruction and limiter are all built and rolled into one. It could be done separately, but we just haven't. But that's not a roadblock for our work, because we do want to move into the world of fully unstructured mixed element grids. We think that's where we can tackle the most complex geometries. So the problem we'll need to solve to take that step is the mapping of the B-spline volume to an arbitrary mixed element unstructured grid. That's the next step we need to take for that part.
Cool. Thank you.
There's also another question in the chat from Hilbert. It says, hi, Rowan, thank you for the presentation. How does the baseline configuration influence the performance? Say, at the start of a design cycle, your baseline could be far away from the optimal. Do you think your adjoint-based method is still a good approach, or would you use a cheaper method to optimize, like a panel method in that case?
Yeah, there's also two ways to answer this. The first part is that the baseline versus where you get to is not really an adjoint issue. That is a gradient-based optimization issue. So you get all the advantages of gradient-based, which is you get to use your gradient and move quickly through the design space. And the disadvantage people whinge about is that you might hit a minima, and the adjoint doesn't address that. That's you're at the mercy of your optimizer. And if you're really worried, you do what people do, which is to start with a different baseline configuration and see if you end up elsewhere. We kind of use the get out clause that mostly what we want to do is just improve on where we started, and we're usually happy with where we land. So do I think the adjoint's a good approach? I guess to answer your question, if you're really worried and want to search the design space even more broadly, you might use a cheaper method to kind of narrow down what is going to be the best, and then move to the higher fidelity method. So I guess that's a question about fidelity, where it RANds fidelity, but you could go to panel methods for a really large, broad design space search.
Thanks. Do we have any other questions from anyone? And I guess we thank you for the great talk, Rowan, and thank everyone for joining us today.
Yeah, thank you for giving up your lunchtime. That's if you're on the East Coast. And thanks for others.
Thank you. Thank you so much.